Okay, let's get started. Welcome back. Hope you are enjoying homework 2. Okay, so today, very exciting lecture, this one and the next one, at least for me. We'll talk about two things. We'll continue the discussion from last time, put it into a more practical direction, talk about achieving the entropy rate for Markov processes, stationary processes, and so on. And we'll dive into like compressing text data. And then towards the end of today's lecture, depending on how much time is left, I will start with LZ77, which is really the most common compression technique you will encounter. And we will continue with that in the next lecture. Okay. So quick recap, right? We talked about a lot of things. So this is just a summary of what you will need really today. We talked about Markov chains. So if you remember Markov chains or Markov processes, for a given k, a kth order Markov process means that you need the previous k symbols to predict the next symbol, but no more. So looking at like further past doesn't help you. In particular, a first order Markov process is the current step depends on the past step, but given the past step, it doesn't depend on anything before that. Stationary processes are like a generalization. They are any process which is time stationary, time invariant, which means that the statistics don't change with time. We mostly will talk about stationary processes only in the context of like certain theoretical results, but in practice, I guess, just think of a process. Given the past, you can predict something about the future. So that's the process in a way. We talked about conditional entropy, which answers the question: given you have two random variables u and v, and given v, how much uncertainty is left in u, right? On average. And then we talked about this specific one, u given v equal to v, which is given you know that your random variable v is equal to v, how much uncertainty is left in u. Or you can talk in terms of bits used, right? So this one says like if I know v, how many bits do I need to compress u? And this one says if I know v equal to v, then how many bits do I need to compress u? And we looked at a few properties. We looked at the chain rule, right? If you remember, where we had like the joint entropy of u and v is simply the entropy of v plus the entropy of u given v, right? We looked at the inequality that conditioning reduces entropy. So just some results we saw, which you will use in your homework. And then we talked about the limit. So you have a stationary process, and what you can do is you take your n plus 1th symbol, you condition it on its entire past, and then you keep increasing n. So in the limit, what will happen is you are trying to capture, given I know the entire past, is there still some uncertainty left in the next symbol? Is each new symbol adding some entropy, some randomness, some bits? And the limit is called the entropy rate. Another equivalent way of expressing it is you think in terms of like a block. So you say, if I take the first n symbols and I take the average entropy, and then you keep increasing n, and then again you take the limit. So and obviously like if you have done limits, you will know that like this will be at the end of the day dominated by the large terms, right? Like the first few terms don't matter. So it's like not very hard to prove that these two are equal. You just need to use stationarity and some properties about limits that you might have seen in calculus. But you don't need that for this class. Okay, so with that in mind, let's quickly do the homework, which will sort of refresh our concepts about conditional entropy, entropy rate, and so on. And then we'll move on. Okay, so we are given a Markov chain in this question. We don't say that it is a stationary Markov chain for now. So how is it described? We say U1 is Bernoulli half. Okay. And let me draw it in this diagram sort of way, which is easier, I think, to understand. So if U1 is 0, we say that U2 has to be 1. Yeah, right? Is that clear? Basically, we are saying that if U1 is 0, then there is no chance that U2 is also 0 because this term is 0. And if U1 is 1, then the next symbol is either 1 or 0 with equal probability. So like this sort of thing. This is 0.5. This is 0.5. So the first question we ask is, what is h of U1? Anyone wants to guess? The entropy of U1. This doesn't even need the class from, like I told you, U1 is Bernoulli half, right? So the entropy of U1 is just 1 bit because it's a Bernoulli half random variable, right? So that's good. Okay. Now I ask you, what is entropy of U2? There was a question on ed I saw where like U2 is dependent on U1. So what do you mean by entropy of U2, right? So at the end of the day, all of these are random variables, whether or not they depend on anybody else, right? So any random variable, you can compute its marginal distribution, you can compute its entropy, right? Just follow the formulas. So what is, for example, what is PU2 equal to 0, right? So we did this last time, so I won't spend too much time unless anybody has questions. So you can like divide it into two cases, right? You do like either U1 was 0 or U1 was 1, right? So you can just split it into two cases. And then you can substitute the things. So half times 0, half times 1. So I guess this is half. No. So U1 is half, okay. Oh, right, this term is 0.5. So this is half, this is half, this is half, this is 0. So I guess you get 1 by 4. Is that what people got? Okay, good. Right, and then you can compute PU2 equal, which is just 1 minus this thing, right? So 3 by 4. So you can compute the entropy, right? This is just the entropy of a Bernoulli 1/4 random variable. Anybody remember the answer? Okay, I will point it. Okay, thank you. Yes. So you have done this a few times now, right? Now, is this process stationary? Anyone?
I thought it was because like it's a Markov chain, so isn't that already stationary?
So is a Markov chain always stationary? That's the question. Not necessarily. That's why like many times in the lectures we specifically say a stationary Markov chain. In any case, in this particular example, you see we said that like stationarity is a very vast property. All statistics stay constant with time, but in particular the entropy should stay constant with time. And you saw that the entropy changed. Entropy of U1 was 1 bit, entropy of U2 was 0.81 bits. So there is no way this can be stationary. A Markov chain is stationary if you start it at a stationary distribution, which was I think question 4. So this is no, because this was actually okay, because HU2 is not equal to HU1. Is that clear? That this is not stationary, right? This was sort of a, don't worry too much about it, but just to make sure the concepts, we are all on board. Then we asked what is HU2 given U1. So let's do this quickly. U1 equal to 0, entropy U2 given U1 equal to 0, right? I think we did an example last lecture, so hopefully you all remember. So this guy, if U1 equal to 0, U2 is deterministic, right? If U1 is 0, U2 is deterministic. And this one is 1, because if U1 is 1, then U2 is Bernoulli half. So after you do the computation, you will see that these two are half obviously, so this will be half, right? If by any chance you didn't get these, look at the last lecture, we did an example, right? And just refresh your probability textbook, and I think they're just following the probability formulas. And now what we did was we changed the initial distribution, which does make it stationary. We didn't ask you to prove it's stationary. You can trust us on that. And we said now you compute the entropy rate, right? And in the last lecture we saw a few things. We saw that for IID, the entropy rate was just the entropy of the first one. For kth order Markov, the entropy rate was just the entropy of uk plus 1 given all the past symbols, right? So in particular for a first order Markov, this is just going to be u2 given u1, right? The entropy of u2 given the past symbol. And now we can compute it using the exact same formula. So let me try to copy paste this one. Right. So again, these stay the same, right? And now the initial probabilities change. So I think you will get 2 by 3 as the answer. Did people get 2 by 3? Yep. Sorry, are you asking a question or? Okay, good. Right. So that's it. Yeah. Just make yourself a bit comfortable, right? This is not just this class. Generally, I think this conditional probabilities you will come across in many, if you do machine learning, for example, or any sort of statistics or probability class. Right. Okay. So moving on to the material. Any questions so far on the quiz on last lecture? Okay. So the question is, how do you achieve the entropy rate? And you will realize it's very simple. So we will first start with a very simple case, the first order Markov source, right? So what is the first order Markov source again? The next symbol depends on the previous symbol. That's it. Okay. So now if you recall, the entropy rate was defined in two different ways when we looked at last time, right? There is this definition and then there is this definition. And for a first order Markov source, the second one reduces to this. Okay. So there are basically two definitions. This one, the first one says that we take the joint entropy of n symbols at a time and then we divide it by n. So this just suggests you do block coding. You just take n symbols at a time, code them together, and as you take bigger and bigger blocks, you are going to achieve the entropy rate just by definition of this thing, right? And we know how to achieve the entropy of this thing by like Huffman coding or arithmetic, any of these codes, right? The other solution is more interesting, and that's the one we'll do most of the time today, is more incremental approach where you actually try to do this conditionally. You take U1, you try to encode U2 given U1, and then you try to encode U3 given U2, and so on. So, so the first one, which is the block coding, is you can just do Huffman on blocks of length n, and then you make n bigger and bigger, and it will achieve the entropy rate. But it doesn't work very well. First of all, you can't make the block size too big, right? The complexity issues we talked about last time. And there is another issue, which hopefully you can understand, which is that when you had your usual IID symbols, right? So you had like U1, U2, U3, U4, and let's say you were like coding in blocks. You took U1 and U2 together, you took U2, U3 and U4 together. This was suboptimal because the Huffman code is only optimal for a dyadic source, right? If you have symbols whose probability is not a power of 2, you don't get the perfect code length and so on. It's not optimal, right? But here, there is another reason why it's not optimal, is that U2 and U3 are correlated. There is some correlation between U2 and U3. So if you're encoding them in blocks separately, you just lose out on the correlation between consecutive symbols. So with that in mind, do this exercise at home just to like convince yourself of these things. But let's not do it now. Anyway, this technique is not something we are going to use. This is the one we are going to use. So if everybody would pay attention, let's recap arithmetic coding. This will be crucial for the rest of this lecture. This is all you need to know about arithmetic coding in this lecture and just in generally, I think, unless you are actually going to implement it. Right. So arithmetic coding, you work with intervals, you divide the intervals into your symbols, and at every step you split the subinterval corresponding to your symbol. Right. So if you have IID model, the thing we have already studied, right, and you have 0, 1, 2, if the first symbol is 2, you take the interval corresponding to 2, you split it into 3 parts, 0, 1, 2, which are proportional to their probabilities, right? And if the next symbol is now 0, you take the interval corresponding to 0 and you again split it into 3 parts corresponding to 0, 1, 2, whose sizes are again proportional to their probabilities. And at the end of this, very easy to see that the length of the interval that you get at the end of the encoding is simply the product of the probabilities. And the way we did the encoding in bits was that the code length was roughly logarithm of 1 by interval length, which was roughly this, log 1 by px1, px2, pxn sort of thing. Let me pause for a minute, make sure everybody understands this because we'll deal with this throughout the lecture. Right. This is like arithmetic coding in a single slide, basically.
But that expected code length that's good like all n symbols together, right?
Yes. So that this thing is for the like n block, basically. Yeah, the entire block. Right. And if you recall our thumb rule, right, we said that for any symbol x, we want to pay basically log 1 by px, and you see that's exactly what arithmetic coding is paying. It's paying exactly log 1 over p for each symbol, right? Okay, so if we are happy with this, and I hope we are, we will okay, so we look at this Markov chain where every symbol can go to either itself or 1 plus that symbol, modulo 3. Look at this figure. We changed something in the previous slide. We changed the arithmetic coding, how it is done. I will wait and ask you to tell me what did we do different now. So we are encoding 2, 0, 1 is what we are encoding. Okay, let's start first. Just for encoding 2, did we do anything different when we are encoding 2 compared to the good old arithmetic coding? I can answer that one. No, we did not, right? Because we just took, we assume the initial thing is uniformly distributed and we just made 3 equal length intervals. Okay, for the next one, anybody wants to tell me, what did we do? What is different from the previous one? Yep.
Basically, I think because 2 can never go to 1.
Yep.
So we didn't have 1, and then the next one, the 2 in that case was gone because you cannot get to 2.
Yeah, very good. Yes. So what did we change? What we changed was, if you know that the first symbol is 2, now your probability model tells you that definitely the second symbol is either 0 or 2 with half probability. So rather than just like following blindly the old distribution, you used a different distribution here. You split the interval according to the conditional distribution, right? You split the interval according to by using the knowledge that the previous symbol is 2. And similarly for the next one, you use the knowledge that the previous symbol was 0. So therefore the next symbol can be either 0 or 1. So just made this slight simple modification in arithmetic coding, which we will see is basically the thing to do. One thing, I think there is a question in the homework where you will see a similar thing. The one where you generate random variables. So just a hint for that. Okay, so if you are happy with that, please let me know if you are not happy with that. If you are not, just trust it's fine. Like you can follow the rest of the lecture, nothing breaks. Okay, right. So we just change the model, right? At every step, instead of splitting the interval by just like the marginal probability, we split the interval according to the conditional probability given the past, right? And in this case, because it's a first order Markov chain, you just need to look at the last symbol, but in general, you can look at the entire past, right? So whatever knowledge you have about the distribution, right, you have seen the entire past. The next time you split the intervals, you use that knowledge. And then you can do the math, which I won't spend too much time on doing, but what you will get at the end of the day is that the expected bits per symbol you get is actually equal to the conditional entropy, which is the entropy rate in this case. Maybe I'll spend a little time. So, right, you remember that the length of the interval for arithmetic coding was a product of the probabilities, right? And in this case, the product of the probabilities, you need to take the conditional probabilities at every step, because that's how we split the intervals. And so the bits for encoding is roughly log of 1 over the, everything else stays the same, right? Like the way you convert intervals to bits stays the same, just the way you split the intervals changes. Yeah, then you do the math. First term is special because there is no past for the first term, but every term after that there is a past. You use your usual formulas, and then you get roughly entropy of U2 given U1. Okay, so this is the generalized version of the thing we just saw. So this is context-based arithmetic coding. This is like the core of today's lecture. You have data, you have a model. The model may or may not be the true model for the data, right? Your data might come from a probability distribution. Maybe your model data does not come from a probability distribution. It's just you are given a sequence and you have a probability model. You have a way to say that if my past was ABCD, then my next symbol is E with probability 50%, like something like that. You have a model like that, right? A prediction model. Okay. First step, you just split your intervals according to the, basically the model has no past. So you just predict the first symbol with the probabilities. Second step, you have one previous symbol. So you predict the probabilities according to the past, the previous symbol. And next step, you basically do the past 2 symbols, and then you take the past 3, past 4, you just take the entire past at every step. So in this example, for example, here you see, for example, that if I know the first 2 symbols are 2 and 0, my model thinks that 1 is more likely to occur than 0 or 2, right? Is that clear? That this is what this model is doing. It's saying that if my previous 2 symbols are 2 and 0, then the next symbol is more likely to be 1 and less likely to be 0 or 2. So it's just splitting the intervals happily according to its probability prediction. The code length will be the log of the 1 over interval length. This didn't change, which is the log of the product of the probabilities. And really this is like the core. Better predictor gives you higher probabilities, right? So if you have a very good predictor, then the thing you actually observe will have very high probabilities, right? If you have a good predictor for English, then it will say that after a Q, you are most likely going to get a U. So better predictor will give you higher probabilities for the thing you actually observe. Higher probabilities lead to larger intervals in arithmetic coding because the interval length is a product of the probabilities, which gives you smaller code length. So the chain is basically better prediction gives you smaller code length. So better prediction gives you better compression. Okay, I will again wait for a second here. And like we are reaching a point where you can now forget about arithmetic coding. Just remember that better prediction gives you better compression, and that's all you need for the rest of the lecture basically. Arithmetic coding is just a tool to get you there. Any questions? Okay. Right, so this is just the same thing written in text. So as long as we can estimate the probability of the next symbol given some context. So context just means the past. Maybe you take the entire past, maybe you just look at the last symbol. Depends on the model. The model can be anything as far as we are concerned. We will look at some specific models shortly. We can use then arithmetic coding to encode the data. And the number of bits used to encode U is just log 1 over p basically. This log rule, the thumb rule we have been seeing, right? This is what you pay. So if you're, let's just like do it more specifically, right? So good model will have p un given past, right? So if it's a very good model, then this will be closer to 1. It will like truly be able to predict strongly that this should be your next thing. And so then you pay basically 0 bits. So that's really nice, right? And if it's a bad model, then the probability, like a bad model would say like after a Q you are never going to get a U. So it will like be very, very bad, a bad model for English, right? And then log of 1 over like very small number is going to be large, right? So if you have a good model, good compression, bad model, bad compression, okay. This is a fun example. So Llama is a language model released by Meta. So I was just trying yesterday. If you take like a word and you try to predict the next word or a next token, and what probability distribution does it give? And I was just like looking at the top 5 guesses. So I looked at Dan, and like the top guess was thanks, I guess, in some new lingo, but okay. I don't know what than is. I see thanking, right? So we see like, but with 18% probability, it thought that THAN would be followed by a X. Okay. Then I gave it more context. I said, oh, it's actually louder than, right? And now suddenly you see that louder than words, bombs, okay. So words got 30.4%, right? So I gave it more context and you see the distribution changed. Now it thinks something different about the next word. Then I said speak louder than, right? So you might already guess where we are going. And I got words. Words is increasing now, close to 50% probability, right? So in this case, if words is the true, true next symbol, can somebody tell me how many bits would I pay to encode words with this model? Roughly how many bits would I pay? Yeah, I see 1, right? Why? Because log of 1 over 2, right? Half is roughly the probability here. This is 1 bit, right? So I'm at a point where given the past 3 words, I'm able to encode the next word, right? A word, if you just naively encode it, would be like a lot of bits to encode. You are just able to encode it with 1 bit at this point. And then I just basically gave it the game, like actions speak louder than, and now you see like word is like 96.5%. It can be now encoded with far fewer than 1 bit. Right. So what did we learn? We learned that the more context you give to a model, if it's a good model, it's going to be able to predict the next symbol with like more and more confidence, right? And therefore it will incur less bits when you try to compress with that model. Obviously we can do this because these models are now very good, right? If you take a silly model like from 20 years ago, just give it long, it won't do anything useful. So, right. Then I tried this, just another simple example. I tried like Stanford's data compression, right? And it suggested research, group, library, team. class was nowhere there, course class, right? Very sad. But then I said enrolling in Stanford's data compression and see how the distribution changes, course, class, program, so on, right? So the longer context you give, usually it will give you better prediction if you're using a powerful model. So that's the lesson, right? So if you know that your data comes from a kth order Markov model, then the previous k symbols are sufficient to predict the next symbol, right? If it's a Markov model, then you only need the previous symbol. You don't need this long history. But in general, for real life data, it's not a Markov model. It's not a kth order Markov model for any k. If you think like you're reading a novel, for example, right? And some character like occurs in the first chapter, and then they might not occur for the last like 5 chapters, and then suddenly occur again. So then like actually having the context of the past 6 chapters is important to be able to guess the name of that character in the last chapter. So there is a limit, like computationally you can't just look at everything in the past, but our brain does that, right, in a way. Like when you're reading a novel, even if something happened in the first, I guess we flip back the pages and look if you don't remember. So, okay, we'll come back to some fun things a bit later. Again, back to the grind, right? Block diagrams. So, everything we just said can be like summarized in this sort of figure where you have a context. Context means past. You have a model. Given the model, given the context, the model predicts the probability of the next symbol, and then the arithmetic coder is able to encode it using these many bits, like for each symbol. And therefore, the total bits you use for encoding is this log loss, the sum of the log loss in a way. Okay, anybody tell me how would the decoding work? Can the decoder, what would a decoder block diagram look like for this thing? Does the decoder need the model? Yeah, I'm seeing some nods. So basically, you remember that arithmetic decoding is very symmetric to arithmetic encoding, right? The decoder also needs to know how to split the intervals. So decoder needs the same model basically. Decoder needs to use the same model, and at step I, it will have the past, right? So decoder will sort of work step by step. At step 0, it has nothing, but it has the model, so it's able to like make those intervals. It decodes U1. Then it knows U1. It feeds U1 into the model. It gets the next step probabilities, decodes U2, and so on. So this is like iteratively able to decode. Right? Is that somewhat clear? And we'll look at some like specific models, which hopefully will make it slightly clearer. And you will have a homework question. Right. So really very symmetric, right? If we wanted to, maybe let's just let's try to draw it. So the decoder. Again, it has the past, U1 to UI minus 1. It has the model. Model gives you the probability. You do a decoding. Right, obviously there is another input, the bit array, right, like the compressed, obviously like it uses the compressed bits, and it then decodes UI. And then this UI becomes your past basically. It goes to your past. So it's like this sort of decoding where the decoder, every step it decodes one symbol that goes into the past, then it predicts the next symbol, decodes the next symbol, then so on. Right, if you make a compressor, like make sure to write a decompressor also, right? Like some of these things, like you can get like compression of 0 bits, everything is good, but then you can't decode it. We will look at some pitfalls for these sorts of models very soon. Okay, I don't have a model. What can I do? I am just getting this data. I don't have a model. Any suggestions? How can somebody explain what they did in homework 1 when they didn't have a model, when they didn't know the probability distribution? The 5th question.
I think we just did like is I think in the home code we would do like I don't know 50 kilobytes and then we would just do blocks and look at like the empirical like distribution.
Yep. So the answer is in question 5 in homework 1. What you did was we were doing Huffman coding back then. You would look at the empirical distribution of the input data, right? You would just make a model from the data and use that to compress the data. We used Huffman there because you hadn't done arithmetic, but you could have done arithmetic coding also. And what was the model you used in that question? Did you assume it was like a Markov model? No, because we used IID back then, right? So we just used a simple IID model, right? So there are 2 ways to go about this. The first way is you first build a model from data and then encode using that model. This is the thing you did in homework. The other way, which we'll look at more this lecture, is adaptive, where you build the model from the data as you see the data, right? So as you see the data, you keep on building a model. I think this is the first time we are doing something like this. Let me show a block diagram before we look at the pros and cons of these 2 approaches. So again, past context, you have a model, but now the model is like not fixed. At every step, the model gives you the probability for the next symbol, you encode the next symbol, and then you update the model. And then you encode, So basically, as the model sees more and more data, it keeps on updating its state. It keeps on updating its own model, basically. The model keeps updating, it keeps training. We will do like a example of this. But for now, can anybody tell me how would you decode in this setting? Is decoding even possible with this sort of thing? What would the decoder need to do? This is adaptive. You are updating the model at every step based on all the data you have seen in the past.
Since the decoder is decoding one symbol at a time, it just needs to update its model accordingly for each symbol it sees. So in that way it keeps it like basically is the same state in the model as the encoder did.
Yep. So the answer is decoder will decode a symbol, it will update. So we can like write it down as like a sequence of operations, right? So you take the decoder, so it will first decode U1, then it will update model. It will need to update the model in exactly the same way the encoder did. At any time if the models diverge, everything is lost. Decode U2, then you again update model. Right, so it basically does exactly what the encoder does, right? They go in sync. And this is very, very crucial. The encoder and decoder needs to share the same state at every step. If at any step the arithmetic coder sees different distributions, it will just break down. Like at any step, if it breaks down, then all the other steps are gone. This is fine for like simple models, but when you like try to do stuff with neural networks and so on, where like all these libraries have all sort of randomness, things just get very bad. It's very hard, like because when you're working with like machine learning applications, right? For ChatGPT, it's not important for a given input to always produce the same output. But for a compression model, it's very important that given a certain input, it should always give you the same probabilities, right? There can't be any like GPU level randomization. There can't be any like floating point stuff. So it's hard. Like people have to write their own libraries if they want to do compression with neural nets, basically. Like even if you write something, then it works on one GPU. So you compress a file on one GPU, you decode it on another GPU, and that breaks. So yes, very crucial. This one is also very important, right? During compression, right, you have the entire input, but you shouldn't get too eager. Don't like straight away update the model with UI before you encode UI. always think of the decoder, right? It's always important to think of the decoder. Whenever each step you think of the decoder, what does the decoder know at this point, right? So let's say the encoder does this. It first updates model with U1 and then it encodes U1. What will happen now? Can the decoder still work? Right, I hear no, right, clearly, because decoder doesn't have U1, right? Encoder has the entire thing, encoder can do whatever, but the decoder can't start. So this is wrong, bad, okay. So it just need to be careful. This comes up in lossy compression also. There are some like these adaptive type schemes, just careful. Last thing is like never provide zero probability to any symbol, because if your model says that this symbol will never occur and then it actually occurs, then log of 1 over 0 is like infinity. So your arithmetic coder will just break basically. So every symbol should, however small it might be, but it should always have a non-zero probability, right? Even if you think that a Q after a Q will never happen in English, provided like some small probability, never provided exactly zero probability. Okay, any questions? Right. So just like a pros and cons list, 2 pass. So one is that we learn model from entire data, right? So you look at the entire data. So maybe you get a better model at the end of the day, and you can parallelize the entire process more, because adaptive is sort of sequential. You're going through the data one by one. In the 2 pass, there are ways to parallelize it. However, you need to store the model in the compressed file. So that's not ideal. You need 2 passes over the data. This is like often a breaking thing in many applications where you can't just hoard data. You have to keep compressing the data as it comes in. You can't keep the entire data in memory. So this is usually a problem. And if your data has like statistics that change over time, right? Like if you have a file which is like start with a novel and then it suddenly turns into a code or something, then the model you learn will be a mixture of the 2 models and it won't do as well. Whereas adaptive might work like even in this case. So adaptive, the nice thing is you don't need to store the model. It is good for streaming. You can compress as it goes. One bad thing is that like initially the model is very bad. You don't know anything. You don't assume anything about the world. So initially you might get like slightly bad compression, but it works well in practice. So we'll look at one example of adaptive shortly. Any questions on adaptive arithmetic coding? Otherwise, I think we'll go to the example in a few slides. Okay. So just like sort of wrapping this up, this relation between compression and prediction that we have been seeing. So if you have done any machine learning class, like either neural networks or without neural networks or AI or whatever, you might have seen this cross entropy loss, also called log loss, for prediction. Right, so for prediction, your task is like you have a bunch of classes and then you're trying to predict which like you're given an image of something and you want to tell whether it's a cat or a dog or a cow. And most of the predictors, what they actually give you is a probability. So they give that 90% cat, 10% dog, 10% cow, let's say, right? And then you evaluate the model according to this loss function where you say that like, so if like this is a cat, right? And the model gives you like cat is 90%, dog is 5, cow is 5. Then the loss you get is like log 1 over 0.9, the probability of being a cat according to the model, right? So this forces the model to give higher probability to the correct symbol and lower probability to the not correct image, and not correct label, right? But this exactly matches the thing we were just doing, right? So actually prediction and compression are exactly the same problem. Not much more to say. Like you can see the loss function is the same. Like it's literally the same loss function. The cost in arithmetic coding of encoding a thing is exactly the same as the prediction loss that we always use in ML. So what this tells you that if you have a good predictor in the ML sense, then it's a good compressor. And compression is all about having a good model for the data. If you have a good model for the data, then you automatically have a good compressor. You don't need to do anything special, right? Many compressors don't actually model the data. Like we'll see the LZ77, the one we'll see, it doesn't like actually model the data, but the compressors we see today will actually model the data. So it need not be explicit, but inherently there is a modeling going on. And final thing, this is sort of out of scope. We won't go into the details, but we are just doing arithmetic coding, right? But in many cases, you can use RANS with some tricks. And people are slowly like trying to use RANS in a lot of these applications. There are some issues, but some of them can be worked out. There is the opposite angle also. Not only does every predictor give you a compressor, actually every compressor gives you a predictor. This is a bit trickier, but it is true. And here the idea is, so if you have a compressor, encodes x1 through xn in L bits, then the predictor that the compressor gives you is basically given by this thing. So basically, each compressor is a predictor, each predictor is a compressor internally. It's like, you remember in the prediction thing, you have log 1 by p. So it's just like you do the formula, right? Log 1 over p. So p is equal to 2 to the minus L. So from any compressor, you can actually create a probability model for your data. This is slightly advanced. We will not worry too much about it, but it is a thing. There is a paper I will tell you about, very recent paper, that actually took like gzip, which is a very common compressor, and turned it into a predictor. Didn't do very well, but you can do these things. Okay. So prediction models used for compression. Okay, so now we'll look at a few specific prediction models, do some like examples, and then do a few very fun experiments. Okay. So this is kth order adaptive arithmetic coding. So what you are trying to do here is you are trying to learn a kth order model for your data as you go through the data. Let's just read the last line. Don't look at the rest of it. I think you will understand from the example the rest of it. So if you have seen BANA in the past several times, and 90% of the times you saw it being followed by a N, so for a banana, for example, and 10% of the time you saw it followed by a L, that is your model basically. The next time you see BANA, you would say that maybe it's a N with probability 90% and L with a probability 10%, right? So just you use the past to predict the future, as simple as that. So let's do an example which should make it clear. So we are doing first order adaptive arithmetic coding. So this means you need to actually keep second order statistics. You will understand why. So initially and this is your data you are going to encode 101011. So initially you assume everything is like 1. You have some frequencies or counts. So you assume that this is to avoid the problem we talked about before, right? When you don't want anything to have a 0 probability. So you assume that you've already seen a 0, 0, you have seen a 0, 1, you have seen a 1, 0, you have seen a 1, 1. You have seen all 4 one time in the past. Okay. So the first symbol you see is 1, and here you don't have a past. So what we'll do is we'll add a 0 at the front, just as a fake 0. Okay, padding. Now, looking at these counts, what is the probability that a 0 is followed by a 1? Like if your past is 0, what is the probability that the next one is a 1? How many think it's 1? The probability that a 0 is followed by a 1. How many think it's 1/3? Half? Very few votes for half. Okay, half is the correct answer, right? So not very tricky, right? So basically what we are doing is this is the equation. The probability that a 0 is followed by a 1 is you take all the cases where you say 0, 1 in the numerator, and you take all the cases where you see 0, 0 plus 0, 1 in the denominator, that sort of thing, right? So basically like what this is saying is you saw like 0, 1 and 0, 1. Like let's say you saw this like 9 times, and you saw like 0, 0 1 time, then you would say that the probability that 0 will be followed by 1 is 9 over 10, right? So just like 9 out of 10 times you are seeing that a 0 will be followed by 1, as simple as that. Okay, and now you have seen a 0, 1, so you update your count. You update your count of 0, 1 by 1, so you do 1 plus 1 equal to 2. Okay, are we happy with this? And then we'll do the next steps, but let me pause for a sec. Okay. Right, and now we do the next symbol. So next symbol is 0. So now you need to, and the previous symbol is 1, right? So next symbol is 0, previous symbol is 1. So you do like probability of 0 given 1 based on this model. Just follow the math. Again you get a half, again you update the model. Okay, let me do the next one, which is more interesting. So now you have your previous symbol is a 0 and next symbol is a 1, right? But remember that due to the padding, you have already seen a 0, 1. So now your model should sort of lean towards, oh, maybe a 0 is more often followed by a 1 and less often followed by a 0. And yeah, that's what it does. It gives you a 2/3 probability instead of a half probability, which it gave you last time, right? So as you see more and more data, it will like learn the statistics of your data and start giving you like predictions which are consistent with your data. And at every step, you keep updating your model. I think you will have a chance to play with this, actually make your own model in one of the homework questions. So that should be exciting. Right, so the idea is that over time you learn the empirical distribution of the data as you see the more and more data, right? And initially you start off with a uniform distribution in the example we did. But if you know something about the data, you can use that to initialize your counts. Make sure encoder and decoder both know, and also make sure nothing is 0, basically. Like never make anything 0, because if you make anything 0, then everything breaks. And one final thing, for that question from homework 1 that you all did, you could have used this with k equal to 0. You could set k equal to 0. So what you could do is, like let's say you have seen 1 0 1 1 0 0 0 1 1 1, and the next symbol is a 0, which is what you want to encode. So in the past you have seen 1 2 3 4 5 6, so 6 ones and 4 zeros. So you could just make a model where this is 4 by 10, and then the next symbol, let's say that's also a 0. Can anybody tell me what will be the predicted probability of the next symbol if this guy had a probability of 4 over 10? 5 over 11 I hear. Yes, I think. Because the last symbol will increase the count of zeros and increase the count of ones, right? So just the counts, nothing special. Okay. So you can implement it. We implemented it. We took the hound of Baskerville and we ran it. Okay. So zeroth order is basically assuming an IID model. First order assumes a first order model, second order, third order. We also ran 2 like standard compressors as benchmarks, gzip and bzip2. Okay, so somebody tell me, why does it improve when you go from 0 to second order? Let's say your input was actually IID. There was no dependence. Do you expect it to improve if you use a larger context? No, right? So clearly there is some relation, and you know that English has, right? English, if you know the past two symbols, you can predict the next symbol better. So therefore, it will improve as you increase the order. Now, can somebody tell me why did it not get better for third order? Why did it actually get worse? Recall that the file has like a certain size. It's like a few hundred kilobytes. It's not infinite. In a smallish file, do you expect to see like a sequence like ABCD or something? Like do you expect to see a sequence of length 4 many times in a very short file, right? If you have a small amount of data, you won't even get any counts. That is the issue. You start with your initial uniform model, and you never get enough counts to like make that model into something useful, because you have such a small, because if you think about it, right, the count array basically, right? So for first order, you need like pairs. You need like xi comma xi plus 1, and then for second order you need like xi plus 1, xi plus 2. You need like 3 at a time, and so on. So this grows like exponentially in the order basically. So if your alphabet size is x and so this is your order, then this is the number of counts you need to maintain. So if you have a very small amount of data, your counts will be very sparse. Most of them will be 0. You won't see most of the patterns. And since you don't see most of the patterns, you get like a very poor predictor, and it doesn't do well. So if you don't have a lot of data, then higher order models start breaking. Because we have a very silly model, right? It just like looks at the past. And so for example, like just as an example, right, like let's say you see like THIN, and then you're trying to predict the next symbol. But if you have never seen THIN in the past, you have no model for it. So it won't do anything useful, right? So unless you have a large enough text where you see that thing many times, it won't learn anything. So that's why it got worse here, okay? And we see that gzip and bzip2 actually beat these models, and we'll talk about them in next lecture. So we talked already about why is order 3 doing worse than order 2. So there are limitations. Kth order becomes slow. The memory grows exponentially in k. The counts become very sparse for large k. As you increase k, the counts just, you don't have many counts, and it leads to worse performance. And this is sort of like a interesting point where just an example, right? Let's say you have THI and capital THI, right? If you had a smart model, it would know that, okay, these two are just the capitalization is different, but there is some relation. If you have seen like THIS many times, even for uppercase T, it should predict that this is, maybe it's the S, right? But if you have that silly adaptive arithmetic coder kth order model, that doesn't know. Everything looks different to it. It has no like understanding of English. It has no understanding of anything. And it just treats any two contexts, any two past sequence as just distinct. Just stores two separate counts for all of them. So doesn't do as well. We can improve them. Okay. I said a lot of bad things. It's not the end of, like people use this. They are used in certain specific scenarios, but they're not the best models. But they're simple models, and you can try them. Okay, now I did another thing. I said, okay, I did the adaptive thing, right? But if I did a 2-pass thing, I can compute the conditional entropy from the data. And now I see, oh, for 0th order, they are very close. For first order, there is a small gap. For third order, the empirical conditional entropy keeps improving. So if I did a 2-pass approach, it seems like I could do a really good job. Like in the Huffman case, you did a 2-pass approach, if you remember. Would you do a good job? What do you think? So if you're doing a third order model, Okay, so let's say in your entire text you see THI only once, right? And it was like followed by S, let's say, in your entire text. So how many bits do you spend to encode S? If you have seen it only once and the one time it was followed by S, you basically, can somebody tell me? None, right? You spend 0 bits. You spend 0 bits to encode the next symbol because you only saw it once, so the probability distribution is deterministic. But how does the decoder know? Yes. Basically what you are doing is the model basically now starts storing the data. As you increase k, what happens is, think of the very extreme. Like let's say you have a text of length 1000, and if you take a 1000th order model, then there is only one 1000 length sequence in the entire input. It has probability 1. You encode it in 0 bits. You don't need any bits to encode it, right? So this is just like a thought experiment where you take, so let's say your input is like 1000 bits, okay, and 1000 symbols, and you take like a 1000 order model. So the probability of the input is 1, probability of everything else is 0, right? You just store your entire data in your model and you say, oh, I encoded it in 0 bits because my model is perfect at predicting my particular data, right? Like you take a Sherlock Holmes novel, your model contains the entire Sherlock Holmes novel, right? And you encode it in 0 bits. You don't need to send anything. The decoder knows it's a Sherlock Holmes novel. So this is silly. This is not how we should do it, right? So, oh no, okay. So as the order increases, basically knowing the empirical distribution basically becomes storing the data in the model. So you're not doing anything smart at that point. You're just storing your data in the model, right? Recall that the model size is like exponential in the order, right? So as the order becomes bigger, the model overwhelms everything. And therefore you need to account for the cost of storing the model. And this is another reason where adaptive models are often preferred, because just you don't need 2 passes and so on. There is this principle, we won't talk too much about it, but like I think this will convey what I was trying to say. Like as you make your model more and more complex, your compressed size will reduce because your model will at some point start learning your data. But the model size will increase exponentially. And so the total size is what you care about, the size of the model plus the size of the data. And there is some point where it's like optimal, like in this figure it's here. At some intermediate model complexity, you will get like the best overall result. This principle is called like minimum description length by Rissanen, who is like one of the people who did a lot of interesting theory in compression. And he is one of the creators of arithmetic coding actually. So good work. Okay, any questions so far? We will, I don't think we'll get to LZ today, but we'll do some fun things. Okay, any questions? So we saw adaptive kth order modeling. We saw what happens if you do a 2-pass and you keep increasing the order. And we saw that the kth order thing has some issues, right? The counts become sparse, it gets harder. So this is something we won't go in too much detail, but it's a great project idea basically if you want to do any of these. So the kth order adaptive is implemented in the library. Solving the sparse count problem. There are a couple of ways where you can actually partially solve that issue. There's something called PPM, something called CTW. And what they do is that maybe I have not seen THI before, but maybe I've seen HI before, or maybe I've seen just I before. So you mix a bunch of things and you try to try to compensate for the fact that maybe you have not seen longer context, but you have at least seen shorter context. So at least use those. Like don't throw away information that you already got. again, not going into details, sadly. Okay, then there are some advanced prediction models. I have links here. I will talk over a couple of them. And really this book is like, if you want to really understand these and implement these, this is like a online textbook by Matt Mahoney, who has done like a lot of interesting work on like heavy duty compressors in particular. Yeah. So all of these are typically the most powerful compressors around, but very slow for many practical applications. Okay, so just very quickly, like two of these advanced models, some of them are neural net based, where what they do is, So it basically like you have given the past symbols, you have a neural network predictor, and then that goes into arithmetic encoder, right? And similarly for the decoder, right? So we just changed our adaptive thing to a neural network predictor, which will again give you the probabilities. And you can do a 2-pass approach, or you can do an adaptive approach. So you can keep updating your neural net. Just like you had a count thing, you can do a neural net thing, basically is what we are saying. For CMIX, the other one I mentioned, this is very advanced ideas where what they do is they have like thousands of different models. You predict based on the last bit, you predict on the last 2 bits, last 3 bits, previous word, first letter of previous word, last letter of previous word, whether this word is the first word in the sentence or the second word, just a bunch of different contexts. And then they have a neural net that mixes all those into like a single probability. There is a talk, I know you won't appreciate from what I just said, but there is a talk from last year's IT forum where the author of this CMIX came to talk. And this is a slide that Pulkit created at some point, which just shows over time how has compression for text improved. And this is gzip, bzip2, 7zip, right? And here we show like, if you assume that the characters are uniform, it's very bad. Bits per character is like more than 4. If you assume like word level some modeling, then it gets lower. And last time we saw some estimate by Shannon where he did some human experiment to try to estimate the entropy rate of English. And we have, as you see on the far right side, we have actually beaten that now. With these CMIX and NNCP models, we are doing better than Shannon's estimate of the entropy rate. So I've really come very far in compressing text. Even though text in many cases is not something, like there isn't a lot of text, like all the text created by humans is like a few terabytes or something. It's far from like the biggest data source, but I think we are just curious to compress text as well as possible. And any questions? Okay, so if you didn't listen to anything, please listen to this because I'm very excited about this. Now, remember that good prediction equal to good compression, right? So today the most powerful predictors are these LLM models, right? So this is new material. We didn't have this last year. So now forget about that MDL setting that we have been working with where like we said that the model is very big, that's bad. No, now we don't worry about storing the model. Just get the best compression. Bring your biggest model. Okay, so throw your most powerful predictor at a problem. Gigabytes, hundreds of gigabytes of model, that's fine. So in a normal setting like this is not useful because where would you store the model? And obviously if you store that model with the file, that doesn't make sense. Can anyone think of any domain or any sort of setting where it's fine to have a very big model as a predictor? So what is the issue with having a very big model as the predictor? We said we need to store the model as part of the compressed file. But do we? Maybe we don't, right? Maybe there is a world where everybody has GPT-4 on their mobile or on their laptop or whatever, right? And then everybody assumes that everybody else has that huge model on their machine and everybody uses that single model to compress things and send it to each other. So there are settings, right? So if you have a large amount of data of the same type basically, and you can afford to deploy the model everywhere, which might become a reality, There are two other reasons to do this. One is that we want to understand the limits of compression. How good can your text prediction become? And other is just to like have fun in a compression class. So for me, the third reason really. Right, so basic model is simple, right? Predictor gives you compressor, log loss. So basically, if you think of LLMs are trained as predictors, and their loss function is the cross entropy loss or 2 power the cross entropy loss. So in effect, they are becoming compressors, right? They are actually compressors. And I took this this recent work by the same person who made NNCP, who made this text compression using large language models, where you can like download any model and then use that to compress your favorite text. And I did like a couple of things. So I took a 2023 novel, and I took second order arithmetic coding. I took bzip2, and I took 2 models, and I took like different context lengths. So context length is like how much of the past number of tokens you see. So you see that if your context length is not very large, if you just look at the last 16 tokens, it does better than bzip2, but not like very impressive. And the medium size model, which is in darker shade of blue, does slightly better than the small model. But it really starts to shine when you take a long context. That's the thing with these large language models, right? They can look at a very big past history and make a very good prediction for the next token based on that. We saw it in the earlier part of the class, if you remember, where the more context you give, the better the prediction becomes. So once you give it like a long enough context, it starts getting to the point where it's like below the Shannon bound, very close to CMIX and NNCP. So it's basically the optimal. And this is a very small model. It's a 430 million parameter model, whereas the GPTs are like tens of billions or more. Any question on this? Like, do you generally understand the idea? Bigger model, better compression, or I guess better model, better compression, more context, better compression, not counting the model size. Okay, now I did this. Instead of like having this English novel released in 2023, I took like Pali is an ancient Indian language. I took this text which was transcribed in Roman script, and I compressed it with again all of these guys. Now you see like actually the models are not able to beat bzip2 or even gzip. Can anybody tell me why? Pali is like Sanskrit, if you've heard of that.
Presumably these LLMs are trained on like they're like a universal model, so they're not really trained for the specific thing, but these presumably will have the model based on the specific distribution.
Yeah. So the idea is that these LLM models, oftentimes the training data set is English, right? Especially for these smaller models, the training data set is limited to like a certain corpus. I didn't try like GPT-4 because I don't have it. It would just take too long, I think, to do. But maybe that will do better. But yes. So gzip, bzip2, second order arithmetic coding, they don't make any assumption about the data. They will work for any type of data. So that is the beauty there, that they are like in a sense, gzip and bzip2 are like universal in a sense. They don't care about your data. They just, for any type of data you give, they will, if it's a big enough sample of data, they will learn the distribution from the data and do a good job. These LLM models, they assume that the data is of a certain distribution, and if your data is not from that, then they do worse. Then Kedar did some experiments where he took an even bigger model, a Llama 13 billion parameter model, on a short story, again released in 2023. He tried different context lengths and he got like different bits per byte, compressed bits per character. Higher context length, better. Nothing changed until now. I guess you can see the number 0.874 is a bit better than the ones we got here. Presumably because the model is stronger. Llama is like a much stronger model than these ones. Then we tried something else. We tried the same model on a Sherlock Holmes novel. And you see this number, 0.2. So earlier we were always talking like around 1 bits per byte. Suddenly you are getting like 0.2 bits, 5x more compressed. So this means either two things. One, either like Sherlock Holmes or like Arthur Conan Doyle's English was much simpler than these modern short story novels, or something else is going on. And any suggestions? why is the compression ratio so good for this new sorry, for this Sherlock Holmes thing on the Llama model. Do you know how the Llama model was created? What did they do to create the model? Nobody? Any guesses? Yeah, they used old books, right? Like among other things, they looked at Wikipedia. So Llama was trained on a bunch of things, including, I assume the Sherlock Holmes thing was part of the training data set. And therefore, I guess it memorized some of it, and it's just doing like an exceptional job at compressing the Sherlock Holmes novel. So one needs to be careful, right, when evaluating. That's why like all of the times we were using this 2023 thing, which we assumed was not part of the very recently released things. Okay, so last slide. Okay, so LLM based compression, remarkable results. It can be, it's really like, we are pushing it to the limit, right? So for a compression perspective, it's just useful to know, even if these are not going to like be the most practical ones. We need to be careful about a couple things we saw. One is that the model and the data, if they are not aligned, then you get not so good results. And when you're evaluating things, just make sure to not use something from the training data. Otherwise, your results might be misleading. Right now, they're very slow and very compute intensive. But actually, like the smaller model that we did, that was like reasonably fast on a GPU. So it is possible that for some applications, these might actually be used in the future.
Can I add a point with you?
Yep.
Yeah, so, but something to notice here is why LLMs even work. Irrespective of like how in machine learning you want to be careful about overfitting and avoid. For the compression sake, if you come up with a model which is really overfitted on whatever you are compressing on, and the model is shared, it's actually a good thing. It's not a bad thing. You might want to overfit and share that model everywhere if you can on the specific data sets you would like to work to. Why in practice it becomes a hard thing to do, because at that point you need bigger and bigger models, you need higher and higher latencies. But for compression's sake, it might not be bad to overfit and pre-share that model on both sides if you can. That's the context in which this LLM-based compression is working.
Yeah. So Pulkit makes a good point where for compression, it's not necessarily a bad thing. Like if you actually want to send a Sherlock Holmes novel to another person, good compression is good, right? It doesn't hurt you. Obviously, like if your model is going to learn everything, then the model gets very big. So there are issues there. But I guess that's why they are so good, because they know everything from the past and still they are able to generalize very well. Even on the latest datasets, they are like state of the art. Okay. So a couple resources. One is this TSZip. So the thing that this one, Kedar ran these experiments. It's a very nice notebook with you will see how we did the thing where we tried to predict the next, like the thing we did at the start, right? Predicting the next token. That's also in this notebook, and how to do compression. However, this one, if you like actually compress it, oh yeah, one thing, just quick note is that when you're like trying to evaluate these things, you know that arithmetic coding will give you this log 1 by p thing, right? So oftentimes we don't even do arithmetic coding. We just calculate log 1, summation of log 1 by p, and we assume that's what arithmetic coding is going to give us, because it has like a 2-byte overhead or something, 2-bit overhead. So that's just like a useful thing to know in practice. Like you don't actually need to do arithmetic coding to know how well your compressor or predictor is performing. Just compute the log loss. And DeepMind had a recent, DeepMind Google, they had a recent paper called Language Modeling is Compression. Very nice title. I think it's an interesting read. Now I think with what you have learned, and if you know a little bit about LLMs, you will be able to understand that entire paper. So I encourage you to take a look. Okay, so next lecture we'll do LZ77, and depending on time, end with like some practical aspects about lossless compression. Thank you.